Okay, let's unpack this. Imagine you've got, say, 6 months of Python under your belt. You're pretty comfortable with prompt engineering, maybe even a wizard at it, and you've already built some really helpful customer support chatbots. Now, picture taking those skills and applying them to something even more impactful. We're talking about creatively and efficiently supporting domestic violence crisis response organizations with AI, taking those chatbots you built, which mostly just react, and evolving them into proactive, intelligent agents.
That's precisely our mission today. You're ready to take that next step, right? To build AI solutions that aren't just functional, but truly robust, ethically grounded, and deeply knowledgeable. So we're going to dive deep into some crucial chapters of the Agentic Design Patterns book. Now, you've built chatbots, they respond to prompts, but agents are a big leap. They're AI systems designed not just to respond, but to actually reason, plan, and execute actions autonomously. They aim to achieve goals, often in complex dynamic environments. And these agentic design patterns we're looking at, they're essentially proven blueprints, best practices for structuring these intelligent agents. They give agents capabilities like problem solving, self-correction, much like how software design patterns provide standard solutions for common programming challenges.
Right, so we're talking about patterns that really transform your AI agents from just being good to being indispensable, especially when the stakes are as high as they are in crisis response. We're focusing on three critical patterns today: exception handling, human in the loop, and knowledge retrieval, or RJ. And the goal here is to give you a kind of mental roadmap to make this documentation, this book, really come alive for you, getting you set up to develop even better AI solutions for that crucial goal. Let's begin charting that roadmap. Kicking us off today, we're diving into a fundamental truth about technology. About pretty much everything, right? Things break. The real world is messy, it's unpredictable. And just like humans, AI agents are going to run into unexpected obstacles, errors, malfunctions. You've probably seen this in your own customer support chatbots, haven't you? Maybe an API call failed or a database just glitched out, leaving your user kind of hanging.
Indeed. And for AI agents to operate reliably, especially in critical domains like domestic violence crisis response, they must be able to manage these unforeseen situations. This first pattern, exception handling and recovery, it's all about developing what the book calls exceptionally durable and resilient agents. It's about ensuring they maintain functionality, operational integrity, despite difficulties and anomalies. This adaptability is critical for agents to function successfully in these complex, unpredictable settings. And it ultimately boosts their overall effectiveness and, crucially, their trustworthiness when you deploy them.
And that trustworthiness, it's absolutely paramount in a crisis situation. When we talk about, say, a crisis bot trying to access a secured database of local shelters, and that database is temporarily down, the immediate thought might be crash or error message. But what's the very first, almost invisible step it would take to prevent that crash from even becoming a visible problem for the user? Because beyond just the immediate loss of support, a system crash in that moment for a survivor, it could inadvertently log sensitive info without safeguards, creating a data breach risk. Or maybe even worse, it could lead to this profound sense of unreliability, make someone hesitant to seek help again, right, when they're already in a vulnerable state. So the insight isn't just about keeping it running, it's about trust and safety on a really deep personal level.
Exactly. And one often overlooked insight, especially in crisis response, is that failure to recover gracefully can actually be more damaging than the initial error itself. If the system just spits out a generic cold error message, it can feel dismissive, uncaring. It erodes that fragile trust a survivor is placing in it. So the real takeaway here is that the recovery itself needs to be empathetic and secure. So when we discuss exception handling and recovery, we're really building that empathetic and secure foundation.
So, okay, what exactly does this exception handling and recovery pattern involve? It sounds like we're basically preparing our AI for every possible mishap that could happen.
That's a pretty good way to think about it, is comprehensive preparation. A pattern really involves two main components. First, you've got strategies for mitigation. These are actions you take when an error happens to sort of reduce its immediate impact and prevent further harm. This includes things like error logging, absolutely essential for a later analysis, and debugging you can't fix what you don't understand, right? Then there's retries. These are great for transient issues, like a momentary network blip, or maybe a service is just overloaded for a second. The agent just tries again. Fallbacks let the agent use alternative methods to achieve a similar goal, so it ensures some functionality is maintained even if the main way fails. Graceful degradation means maintaining partial function even if full recovery isn't immediately possible, still offering some value to the user. And of course, notifications alerting humans when their intervention is needed, especially in critical situations. Then, the second component is mechanisms for recovery. This is more focused on restoring the agent to a stable operational state after the immediate error crisis has passed. This could involve state rollback, which means undoing any changes made by a failed action. Really important for data integrity. Diagnosis is about understanding the root cause of the error to prevent it happening again. Learning from mistakes is key. Self-correction or replanning means the agent adjusts its own behavioral logic to avoid repeating that mistake. And finally, escalation. Delegating complex or severe issues to a higher authority, which, let's be honest, is often a human operator. Recognizing the limits of the AI's autonomy.
Right. So it's about making your AI robust enough to function, maybe even thrive in these unpredictable environments. So back to that crisis bot trying to access the shelter database. If it's down, instead of just crashing, it uses these mechanisms. It might try again, maybe use a fallback to offer a national hotline instead, or gracefully degrade by saying, I can't check local availability right now, but here's general safety info, all while keeping a calm, reassuring tone for the user. Okay, let's break down the 3 core phases of this pattern. The documentation has a figure, but let's talk through it. Starting with detection. How do we even know there's a problem brewing?
Yeah, error detection is all about meticulously identifying these operational issues as they arise, often, hopefully, before they impact the user. This can happen in a few ways. Maybe an external tool gives back an invalid or, malformed output, or you get specific API errors, like a 404 not found when you try to get a resource, and maybe a 500 internal server error from some backend service you rely on. Other critical signs could be unusually long response times from services or APIs. That can indicate a problem. Or the book calls incoherent and nonsensical responses, the stuff that just deviates completely from the expected format or content. These are all kind of explicit signals that something's wrong, often triggered by validation checks you build into the AI's output or its tool responses.
And it's not just passive, right? You mentioned you can even implement proactive monitoring. Maybe have other specialized agents whose whole job is to watch for problems before they escalate. Sort of like a smoke detector for your AI system, constantly sniffing for trouble. So for your crisis bot, if it tries to connect to that external API for real-time legal aid info and gets a 404 resource not there, or maybe its own internal risk assessment tool just returns gibberish. That doesn't make any sense given the context. That's error detection in actions, the first crucial step, like the tripwire that alerts the system.
Absolutely. So once an error is detected, the next phase is error handling. And this is where having a really carefully thought out response plan is essential to mitigate that immediate impact. This involves several key strategies we touched on: logging, meticulously recording all the error details, timestamps, inputs, outputs, error messages, everything. For later debugging and analysis, that log is your forensic tool basically for understanding what went wrong and improving the agent. Retries, as we said, attempting the action again, maybe with slightly adjusted parameters or after a short delay. Really useful for those transient network issues or temporary service hiccups that often just fix themselves. Then you have fallbacks, where the agent uses alternative strategies or methods to make sure some functionality is maintained, even if the primary method fails, like using a cached version of data if a live API call bombs out. Graceful degradation means, okay, if complete recovery isn't immediately possible, the agent can still provide partial functionality. Maintain at least some value for the user. Think of it as providing the essential info, even if specific details are temporarily out of reach.
And finally, notification. Alerting human operators or maybe other agents for situations that really need human intervention or collaboration, especially if the issue is critical and all the automated recovery paths have been tried and failed.
Let's put on our crisis response hats again for a second. If that crisis bot can't find a specific local shelter because of a database error, a fallback might be to offer a broader regional hotline number, still providing a pathway to help, right? Graceful degradation could mean the bot says something like, I'm having trouble accessing specific shelter information right now, but I can still offer general safety planning advice. It keeps the conversation going, maintains support. And obviously, notifying a human supervisor if it's a critical failure ensures no one is left hanging without support for too long.
Right. And the final phase here is recovery. This is all about restoring the agent or the system to a stable operational state after an error has been handled. This could involve state rollback, like we mentioned, reversing recent changes or transactions to undo the effects of the error, ensuring data integrity. Super vital in situations where partial updates could corrupt critical information, like a safety plan. A thorough diagnosis into the root cause of the error is vital for preventing it from happening again. We want to learn from these mistakes and continuously improve the system. Then there's self-correction or replanning. This is where the agent adjusts its own plan, its logic, maybe its parameters, to avoid repeating that same error in the future. It adapts its behavior based on the failures it sees, and in really complex or severe cases, escalation is key. Delegating the issue to a human operator or maybe a higher-level system when it's just beyond the agent's current autonomous capabilities ensures appropriate human oversight.
Okay, so imagine your bot is trying to update a user safety plan details in a database, and the update fails halfway through. A state rollback would undo those partial changes, preventing corrupted or incomplete data. That makes sense. Then the bot might self-correct its approach for future attempts, learning from that failure. Or, for truly complex situations, say, a really nuanced legal question about child custody that needs deep legal interpretation, it would escalate the whole interaction to a human crisis counselor. This ensures the user always gets the most appropriate support, and the system actually gets smarter with every error it handles.
Exactly. And this isn't just theory, right? It's fundamental for real-world deployments across all sorts of sectors. Customer service chatbots managing database errors, trading bots handling financial errors, smart home agents addressing device malfunctions. They all benefit hugely from robust exception handling. It's really about building agents that are not only intelligent but also reliable, resilient, and frankly, user-friendly when they face these real-world complexities.
So how would this specifically manifest in the domestic violence crisis context? Can you give us a few more concrete scenarios, like day-to-day stuff?
Certainly. Let's take that customer service chatbot within a crisis hotline again. Imagine it's trying to access a database of emergency contacts, maybe police precincts or specific advocate numbers. If that database is temporarily down, it shouldn't just give up or crash. It detects the API error. It informs the user gently about the temporary issue, something like, "Our local resource database is currently experiencing a slight delay. Please bear with us. We're working to restore it quickly." End quote. It might then suggest trying again in a moment. Or, and this is crucial, it could immediately escalate the query to a human agent who might have access to alternative, perhaps even manual resources or lists. This ensures that continuous support and prevents a service disruption right when someone needs help. Or think about a data processing agent. Maybe it's compiling anonymous statistics on the types of calls received, perhaps to identify trends for training or reporting on service utilization to secure funding. If it encounters a corrupted log file while processing a batch of records, it shouldn't just halt the entire vital process. Instead, it should skip that single corrupted file, log the error details meticulously for a human to investigate later, continue processing all the other valid files, and then report the skipped ones at the end. This allows the overall data collection to proceed without interruption, making sure critical insights are still gathered and no valuable data is lost just because of one bad entry. One more. Maybe a proactive outreach agent. Let's say it's programmed, with consent, to send a follow-up message after a certain period, checking in. If the messaging API it uses fails, it shouldn't just give up. It should log the failure, retry sending the message according to some predefined schedule, and if it continues to fail after several attempts, it should definitely escalate to a human operator. This ensures that vital communication is delivered, especially when it concerns safety planning or just checking in on a survivor's well-being. You don't want those messages lost.
Okay, let's look at a concrete code example that shows this in action using the Agent Development Kit, the ADK. This code defines a sequential agent, which, you said, means the agent's inside run in a guaranteed order, and it's designed to retrieve location information robustly.
Right, so here we have three sub-agents working together in a sequence. The primary handler is the first agent in line. Its job is to try and get precise location info using a specific tool, maybe a precise geolocation API. If that fails for any reason, maybe the API is down, maybe the user's input was ambiguous, the fallback handler steps in next. This agent checks a special variable in the agent's memory, the state, called state primary location failed. If that variable indicates failure, it then tries something else. It extracts just the city from the user's original query and uses a different, perhaps less precise tool like get general area info to find broader but still useful location information. Finally, the response agent takes whatever result was stored in state location result, whether from the primary or the fallback, and presents it to the user. It might even apologize gracefully if no information could be found at all. The sequential agent structure guarantees this exact order of operations. Try the best way first. If that fails, try the backup. It builds resilience layer by layer.
And you can apply this directly to your crisis bot, right? Your primary handler might try to find a specific local resource for the user's current location, like a shelter with confirmed open beds right now. If that fails, maybe there's no local match in the database, or the service providing real-time bed availability is down, down, round. The fallback handler could then automatically search for regional or national resources, or maybe offer broader general advice like, here's how to create a safety plan online. The response agent then presents the best available information it could find, always ensuring the user gets some form of assistance, preventing those frustrating dead ends. It's a perfect example of building these layers of resilience right into your AI solution's logic. So, the big picture here. Exception handling and recovery isn't just a nice to have, it's absolutely essential for building robust and reliable AI agents, especially in these high stakes environments where failures can have really profound human consequences.
Absolutely. It involves systematically detecting errors, handling them gracefully, and implementing these well-defined recovery strategies. Detection includes actively validating tool outputs, meticulously checking API error codes, maybe using timeouts to prevent the agent from getting stuck waiting forever. Handling involves comprehensive logging for forensics, retrying for those transient issues, having fallbacks ready as alternatives, enabling graceful degradation for partial functionality when needed, and setting up clear notifications for human alerts. And recovery focuses on restoring stable operation through careful diagnosis, enabling self-correction where possible, or ensuring timely escalation to human experts when necessary. This whole pattern ensures your agents can operate effectively, even in the unpredictable and demanding environments like domestic violence crisis response, where consistent, reliable support is absolutely paramount.
Okay, so as we chart this mental roadmap, we've basically secured our agents against crashes and unexpected detours with exception handling. That's resilience. But our journey isn't just about avoiding technical problems. It's about navigating the inherently human terrain of ethics, empathy, and judgment, which AI, let's face it, struggles with. That's where our next major landmark on the roadmap comes into view, human in the loop, or HITL. It seems to be about recognizing the irreplaceable value of human judgment, ensuring AI never operates truly alone, especially when things get sensitive.
Precisely. HITL deliberately interweaves human strength. Things like nuanced judgment, creativity, deep empathetic understanding with the AI's computational power and efficiency. It's really not about replacing humans. It's fundamentally about augmenting human capabilities, making humans better, faster, more effective. This strategic integration is often a necessity, especially as AI systems get embedded deeper into critical decision-making processes where you have clear ethical boundaries or significant risks involved. In domains like domestic violence crisis response, full AI autonomy. Well, it might be imprudent, even dangerous, because humans provide that essential empathy, ethical judgment, and creative problem solving that AI currently lacks, especially in highly emotional and complex situations. It's about achieving a powerful synergy where the AI elevates human potential without losing that essential human touch.
Robust, ethically grounded, deeply knowledgeable. Those are powerful aspirations for AI. But how realistic is ethically grounded when we're dealing with AI, which fundamentally lacks human consciousness, right? Is it truly about making the AI itself ethical? Or is it more about building systems that reflect and enforce human ethical guidelines through clever design, especially in such sensitive areas?
That's a really crucial distinction to make. It's definitely not about making the AI itself ethical in some philosophical sense. That's probably not even possible right now. It's about meticulously designing the system to embody and enforce human ethical guidelines, particularly around safety, privacy, and the principle of non-maleficence, doing no harm. The HITL pattern is a primary mechanism for doing exactly that. By baking human oversight and intervention directly into the process, we ensure that human values remain the ultimate decision point in critical moments. This way, the AI acts as a powerful tool that is guided by human ethics, rather than autonomously generating its own potentially flawed ethical framework.
Okay, so how does the symbiotic relationship actually work in practice? What are the key components when we're talking about embedding those human ethical guidelines into the system's operation?
Well, the HITL pattern integrates human intelligence with AI in several key ways to enhance agent capabilities. It acknowledges that optimal AI performance, especially in sensitive contexts, often requires this careful blend of automation and human insight. It encompasses several key aspects. First, human oversight. This means monitoring AI agent performance and output, maybe through reviewing logs, maybe via real-time dashboards to ensure it's sticking to guidelines, preventing undesirable outcomes, and spotting subtle signs that maybe the AI is drifting off course. Second, intervention and correction. This happens when an AI encounters errors or maybe ambiguous scenarios it can't resolve, and it actively requests human help. Operators can then step in to rectify errors, supply missing data, or guide the agent. And crucially, this intervention also provides valuable data to improve the AI in the future. Then there's human feedback for learning, where collected feedback is used to refine the AI models, influencing their learning. This is exactly what happens in reinforcement learning with human feedback, RLHF, where human preferences directly shape the agent's learning trajectory over time. This is how the AI gradually learns to become more aligned with human values and expectations. Fourth is decision augmentation. Here, the AI provides analyses, summaries, maybe recommendations, but the human makes the final critical decision. This enhances human decision-making with AI-generated insights without replacing ultimate human accountability. Fifth, human-agent collaboration. This involves cooperative interaction where humans and AI agents contribute their respective strengths. Maybe agents handle routine data processing or initial info gathering, while humans manage the creative problem-solving, the complex negotiations, or the deeply empathetic conversations. And finally, arguably one of the most important parts, escalation policies. These are clearly established, unambiguous protocols that dictate when and how an agent must escalate a task or a conversation to a human operator. This prevents errors in situations beyond the agent's capability and ensures a seamless, informed handover when human expertise is required.
Right. So thinking about your crisis bot again, it could maybe efficiently handle that initial information gathering, asking about the user's immediate needs, providing general info on legal rights from its knowledge base. But then, if the user expresses complex emotional distress or maybe reveals a high-risk situation that requires a really nuanced, empathetic response, the bot follows that clear escalation policy. It hands off immediately to a human counselor. This ensures the user gets the right level of support at exactly the right time. It's a structured way to make sure no one falls through the cracks when the situation gets tough.
Exactly. But while HITL is immensely beneficial, it's not without its challenges. And understanding these is really key to implementing it successfully. A primary one is the lack of scalability. Humans simply cannot manage millions of tasks or conversations individually. This creates a fundamental trade-off between automation, which gives you scale, and HITL, which gives you high accuracy and nuance through human judgment. Finding that right balance, deciding precisely what to automate and what absolutely needs to remain human-led is crucial. Another big challenge is the dependence on expert operators. The effectiveness of HITL really relies heavily on the expertise of the humans in the loop. For instance, you need a highly skilled crisis counselor to accurately identify subtle cues in a text conversation, to understand the emotional subtext, maybe pick up on veiled threats or risks, and provide the correct guidance when the AI flags a nuanced or potentially dangerous situation. Without that high level of human expertise, the intervention might not be as effective or could even inadvertently be harmful. And lastly, maybe most importantly in this context, are the privacy concerns. These are profoundly significant, especially in the domestic violence crisis domain. The information shared can be intensely personal, vulnerable, legally sensitive. So, sensitive information must often be rigorously anonymized or de-identified before it's ever exposed to a human operator, even an internal one. This adds a significant layer of process complexity that is absolutely non-negotiable. It requires really thoughtful, legally compliant design to protect the individual seeking help. And furthermore, in this specific domain, you're not just dealing with general data protection rules like GDPR or HIPAA. You're also grappling with complex nuances around mandatory reporting laws, the tricky issue of implicit consent in a crisis situation, and the ongoing potential for re-identification if data isn't handled with extreme care, especially when combining information for a human agent. It's a genuine minefield that demands legal and ethical counsel right alongside the technical expertise. It's probably one of the most challenging aspects of implementing HITL responsibly here.
Yeah. For a domestic violence crisis organization, these caveats feel particularly acute. You have to carefully balance helping as many people as possible, that's the scale part, with ensuring the absolute highest quality, most empathetic, and completely confidential support. That's the accuracy, expertise, and privacy side, and that privacy aspect alone.
Wow. It requires extremely thoughtful design and meticulous implementation because you're dealing with such deeply personal and sensitive situations where mistakes aren't just data breaches. They can have devastating real-world consequences for someone's safety. So this pattern, HITL, it's vital across industries, especially where accuracy, safety, ethics, or that nuanced understanding are paramount. How does it translate into tangible applications that our listener could build or contribute to?
Absolutely. Think about content moderation platforms. AI flags potential hate speech or inappropriate content automatically, but the ambiguous cases, the ones with subtle context, maybe sarcasm, maybe local slang, they get routed to human moderators for that final review. That's HITL, or financial fraud detection. AI flags suspicious transactions based on patterns, but human analysts investigate those flags, bringing their experience and intuition to bear, making the ultimate determination. That's HITL2. And a direct parallel for your work is customer support for complex queries. A chatbot handles the routine stuff. What are your hours? Where can I find info on restraining orders? But if the user problem becomes too complex, too emotionally charged, or requires empathy, nuanced understanding that the AI simply cannot provide, the conversation must be seamlessly handed over to a human support agent. This ensures both efficiency for routine tasks and critical human intervention when it matters most, providing that essential lifeline. Another application could be legal document review agent. Imagine an AI that can quickly sift through vast amounts of legal text, maybe summarizing case law or identifying relevant statutes. But a human legal expert would definitely be in the loop to review the AI's interpretations, especially for sensitive cases involving survivor rights or custody, to ensure absolute accuracy and compliance with current legal precedents, which can change rapidly.
Now, there's a fascinating variation mentioned in the book called Human on the Loop. It sounds slightly different. Here, human experts define the overarching policy, the big rules, and the AI then handles the immediate actions autonomously to make sure those rules are followed. It's like setting the strategic direction and letting the AI handle the high-speed tactical execution.
That's a great way to put it. Consider an automated financial trading system. A human expert, a portfolio manager, sets the investment strategy, maybe something like maintain a portfolio of 70% tech stocks and 30% bonds, and automatically sell any stock that falls 10% below its purchase price. That's the policy. The AI then monitors the market in real time, 247, and executes trades instantly based on these rules, perhaps millions of times a second, without needing human approval for each individual trade. The human sets the high-level, slow-changing policy, and the AI handles the high-speed, immediate actions. Or think about a modern call center. A human manager establishes high-level routing policies. For example, any call mentioning the phrase service outage must go directly to technical support, or if the sentiment analysis of the caller's voice indicates high frustration for more than 60 seconds, the system should automatically offer to connect them directly to a human agent. The AI then interprets customer needs and sentiment in real time and autonomously routes calls or offers escalations based on these human-defined, often quite complex rules. The AI manages the high volume of immediate actions according to the strategic guidance provided by the human manager.
Okay, this feels incredibly relevant. For our listeners' crisis organization, how does this human-on-the-loop principle specifically address a unique challenge they might face? Like, how could they apply this?
Well, for your crisis organization, a human manager or a senior crisis expert defines the critical safety policy. For instance, if a user mentions keywords like immediate danger, threats to safety, or specific phrases indicating suicidal ideation, the system must immediately route the conversation to a live human crisis counselor without any intermediate AI steps or questions. That's the policy. Your AI system then handles the initial interactions, perhaps gathering basic context, but it's constantly analyzing the user's language in real time. The moment it detects a trigger matching that critical human-defined policy, it autonomously executes the escalation. Instantly. This ensures a rapid response when seconds literally count. It's how you embed that crucial human expertise and non-negotiable ethical guidelines directly into the AI's operational logic, creating a system that prioritizes safety above absolutely everything else.
Let's look at a code blueprint again. This time for a technical support agent in the Agent Development Kit, the ADK, that actually incorporates HITL, specifically using an escalate model-to-human tool. This gives you a tangible example of how these concepts translate directly into code you could write.
Right, this code offers a pretty clear blueprint for an ADK agent designed around this HITL framework. We have a technical support agent that's configured with specific instructions, its persona, and crucially, it's equipped with a set of tools. These tools include things like troubleshoot issue, maybe create ticket in the support system, and, most importantly for this pattern, the Escalato Human tool. This Escalato Human tool is a core part of the HITL design. It ensures that complex, emotionally charged, or highly sensitive cases get passed promptly to human specialists when the AI recognizes its own limitations. It provides that clear, defined path for the AI to essentially know its limits and ask for help. Now, a really key feature of this particular architecture is its capacity for deep personalization. This is achieved through a dedicated callback function, here called personalization callback. Before the agent even contacts the LLM to generate a response, this callback function dynamically retrieves customer-specific data, things like their name, maybe their support tier, their purchase history directly from the agent's internal state or memory. This relevant context is then automatically injected into the prompt as a system message. This enables the agent to provide highly tailored and informed responses that reference the user's specific history, leading to a much better, more informed, and frankly more empathetic user experience.
Okay, and this code is directly adaptable for your crisis bot. Imagine your bot detecting a user's high level of urgency, or maybe a keyword indicating severe risk, like fear for my life. That escalate a human tool will be called immediately. But even more powerfully, that personalization callback concept. It can be adapted. You could use it to retrieve relevant, crucially, privacy-compliant historical information about the user's previous interactions. Of course, this would require explicit user consent and adherence to all legal and ethical guidelines for handling sensitive data. But if you have that, you retrieve it from the state. This means if a user has sought help before, maybe talked about a specific situation, the human counselor they're escalated to will have that immediate sensitive context right there. It creates a much more empathetic and efficient handover. It transforms a potentially jarring cold transfer into a warm, informed continuation of support, maintaining that crucial continuity of care. So the core idea here really is a partnership. AI does the heavy lifting, the pattern matching, the initial triage. But humans provide the critical judgment, the empathy, the ethical oversight.
Absolutely. The human-in-the-loop pattern is fundamentally about integrating human intelligence and judgment seamlessly into AI workflows. It's crucial for ensuring safety, ethics, and overall effectiveness, particularly in these complex or high-stakes scenarios like crisis response. Key aspects include establishing clear human oversight, designing mechanisms for intervention and correction, incorporating human feedback for continuous learning and alignment, using AI for decision augmentation rather than full autonomy, and especially defining those robust and transparent escalation policies. And while it definitely has drawbacks, scalability issues, a strong dependence on expert operators, and those critical privacy concerns that need very careful management ultimately, HITL allows for responsible AI deployment and continuous improvement. It ensures human values remain absolutely central to intelligent system design, particularly in sensitive domains where they matter most.
Okay, our agents are resilient thanks to exception handling. They know when to ask for human help thanks to human in the loop. That's huge progress. But there's another challenge, a really fundamental one. Large language models, for all their brilliance with language, are fundamentally limited by their training data. It's kind of like having a brilliant friend who only knows what they read, say, a year ago. Impressive, sure, but not always current, and certainly not special.
That's a perfect analogy. LM's knowledge is essentially static. It's frozen in time to the moment their training data was collected and processed. This means their internal knowledge doesn't include real-time information, specific company policies, or highly specialized details unique to a particular domain, like, say, the specific procedures of your local courthouse regarding protection orders. This limitation frequently leads to outdated or inaccurate responses. And critically, it can lead to those infamous hallucinations where the LLM confidently generates false or nonsensical information, which is completely unacceptable, especially in a crisis situation where misinformation could be dangerous.
And that's precisely where knowledge retrieval, or RG, which stands for Retrieval Augmented Generation, comes in. It's kind of the superpower that lets your AI look up information on the fly, almost like a human consulting a specific book, searching a trusted database, or even searching the live internet. It transforms the AI from just a fluent conversationalist into an effective data-driven tool. It grounds the AI's responses in verifiable reality, in facts.
Indeed. And just imagine the consequences otherwise. Imagine your crisis bot providing outdated legal advice because its training data is from 2 years ago and the law has changed, or suggesting a local support resource that unfortunately no longer exists in your community, or giving generalized advice about safety planning when a specific local law or resource offers a much better tailored option. That's simply unacceptable in a crisis. The danger isn't just inaccuracy, it's potentially misleading someone at a critical juncture, eroding their trust, and maybe even putting them at further risk. RAG is how you keep your bot's information accurate, current, and verifiable for those who need it most. It's fundamental for ensuring reliability and building that essential trust. Okay, so the knowledge retrieval, or RAG pattern. It significantly enhances the capabilities of LLMs by granting them access to external knowledge bases before they generate a response. It's a pre-processing step, essentially. When a user poses a question, it isn't sent directly to the LLM's brain. Instead, the system first performs what's called a semantic search on an external knowledge base. This knowledge base could be a library of your organization's documents, internal databases, maybe even curated web pages. Semantic search means it understands the meaning of the query, not just looking for exact keywords. It leverages those embeddings we'll talk about in a sec. The system then extracts the most pertinent snippets or chunks of information from this knowledge base related to the query's meaning. These extracted pieces then, augment, basically. They're added to the original prompt. This creates a much richer, more informed query that essentially gives the LLM an open book to answer from, right there in its input. This enhanced prompt is then sent to the LLM. With this additional relevant context directly in its input, the LLM can generate a response that is not only fluent and natural sounding, but also factually grounded in the retrieved data, rather than relying solely on its potentially outdated or generic internal knowledge.
The benefits here sound huge. You get access to up-to-date information, which immediately overcomes the limitation of that static training data. It seems like it would drastically reduce the risk of hallucination because the responses are grounded in verifiable facts you provided. It allows access to highly specialized, maybe even proprietary knowledge like your specific internal policies for handling certain crisis situations, knowledge that would never be in a general LLM's training set. And a vital advantage, especially for building trust, is the capability to potentially offer citations, pointing back to the exact source document where the information came from. That seems crucial for accountability, especially in sensitive contexts where accuracy is absolutely paramount. Okay, to really grasp RAG, let's understand some of the key concepts behind it. Starting with how text becomes data that an AI can actually understand and search effectively.
Right, first up are embeddings. In the context of LLMs and RG, embeddings are numerical representations of text, could be words, phrases, sentences, or even whole documents. Think of them as vectors, which are essentially just lists of numbers, often hundreds or thousands of numbers long. The core idea is to capture the semantic meaning and the relationships between different pieces of text within a mathematical space. Words or phrases that have similar meanings will have embeddings that are located closer to each other in this high-dimensional vector space. For instance, the vector for cat and the vector for kitten would be very close mathematically, while the vector for cat and the vector for car would be far apart. This allows the AI to understand not just the words being used, but their deeper conceptual relationships.
Ah, okay. So this is how your bot can understand that a user saying help with abusive relationship and another user saying support for intimate partner violence actually mean pretty much the same thing, even though they use different words. It sees the underlying meaning captured in those vectors, not just the exact phraseology. That's critical for understanding nuanced human communication, especially in a crisis where language might be indirect.
Exactly. And this leads us directly to text similarity and semantic similarity. Text similarity is just a measure of how alike two pieces of text are. Now, lexical similarity is surface level, based mainly on overlapping words. But semantic similarity, which is what we care about for Arabic, is a more advanced form. It focuses purely on the meaning and the context of the text. It aims to understand if two pieces of text convey the same concept or idea, regardless of the specific words used. Semantic distance is just the inverse of this, how far apart two meanings are. In Arabic, the semantic search process relies on finding documents or chunks whose embeddings have the smallest semantic distance to the embedding of the user's query. This ensures true conceptual relevance, not just keyword matching.
Right. So a good system recognizes that what is the capital of France and which city is the capital of France are asking the exact same question, semantically. In raw reg, this smart search capability is what allows it to find relevant information, even if the user's exact phrasing isn't explicitly present in your knowledge-based documents. It's incredibly powerful for dealing with the dynamic, often imperfect way humans actually communicate.
Okay, next concept, chunking of documents. This is the practical process of breaking down large documents, like long legal guides or detailed policy manuals, into smaller, more manageable pieces, or chunks. Crucially, you do this while meticulously trying to preserve the context of the information within each chunk. Why is this important? Because LLMs, especially within their operational context windows, the amount of text they can process at once, cannot efficiently handle entire large documents. They have token limits. Instead, the RAG system works with these smaller chunks, retrieving only the most relevant ones based on the query and feeding only those to the LLM. And the way documents are chunked, the size of the chunks, whether they overlap, is really crucial for maintaining the meaning and usefulness of the information. For instance, you wouldn't want to split a critical safety instruction right in the middle.
Absolutely. And for your crisis bot, that chunk size parameter you mentioned in the LangChain example, it feels like a crucial tuning knob. If the chunks are too small, maybe important safety protocols or legal steps get fragmented across multiple pieces, losing vital context when retrieved individually. But if the chunks are too large, the LLM might struggle to find the precise legal detail a survivor needs within that big block of text. Or it uses up too many of its thinking tokens, its context window, and becomes less efficient or accurate. And that chunk overlap setting, it's like ensuring a smooth handoff between chunks, right? Where the end of one chunk slightly repeats at the start of the next. So you don't accidentally lose the flow of a critical legal explanation or a multi-step safety plan when a query happens to fall near a chunk boundary. So for that 50-page legal guide for survivors, chunking it into logical sections like emergency protective orders, housing assistance, child custody allows the RD system to retrieve only the most relevant section when a user asks a specific question. This makes the information provided to the LLM much more focused, faster to retrieve, and ultimately more accurate and helpful for the user's immediate need.
Precisely. Now, to store and efficiently query all these embeddings you've created from your chunks, we use vector databases. These are specialized databases designed precisely for this purpose. After your documents are chunked and converted into those high-dimensional embedding vectors, these vectors are stored in a vector database. Unlike traditional databases that rely on keyword-based searches, vector databases excel at semantic search, finding results based on conceptual meaning based on that vector proximity we talked about. When a user's query is also converted into a vector, the database uses highly optimized algorithms like HNSW, which stands for Hierarchical Navigable Small Worlds, a fancy name for a clever graph-based indexing method to rapidly search through potentially millions or even billions of vectors. Think of HNSW like building a network of interconnected shortcuts between all your data points in that high-dimensional space. It allows the database to instantly jump to the most relevant areas instead of having to sift through everything one by one, which would be incredibly slow. This approach is far superior for our age because it uncovers relevant context even if the user's phrasing is completely different from the source documents. Popular examples include Pinecone, Weaviate, ChromaDB, and others.
Okay, so these vector databases are really the engine powering Archie. They allow your bot to rapidly find that meaning-similar information. So if a crisis survivor asks something vague, like feeling unsafe at home, the vector database can quickly pull up chunks about safety planning, emergency shelters, maybe legal options, even if those exact words aren't in the database entries, because it understands the underlying concept of seeking safety from domestic abuse. That's truly powerful.
And finally, just to touch on it, we have retrieval techniques. While vector search, semantic search using embeddings, is the primary method used in modern RAG, an older but still valuable technique is BM25. This is more keyword-based. BM25 is excellent for finding documents with very precise keyword matches. Sometimes you do want that. So, to get the best of both worlds and ensure really robust retrieval, hybrid search approaches are often used. These combine the keyword precision of BM25 with the deep contextual understanding of semantic vector search. This fusion allows for more robust and accurate retrieval overall, capturing both literal keyword matches and broader conceptual relevance. Now, despite its power, the RAG pattern is definitely not a magic bullet. It comes with its own set of challenges you really need to be aware of when implementing it. A primary issue is fragmented information. The complete answer to a user's query might actually be spread across multiple different chunks or even different documents in your knowledge base. The retriever might find some, but miss other crucial pieces of context, leading to an incomplete or potentially inaccurate answer from the LLM. Closely related is the quality of chunking and retrieval. We talk about how important chunking is. If your chunking strategy is poor, or the retriever pulls back irrelevant chunks alongside the relevant ones, it can introduce noise. This noise can confuse the LLM, making its final response less precise, or worse, causing it to latch onto the wrong information and hallucinate an incorrect answer. Another significant hurdle is dealing with contradictory sources. What happens if two different documents in your knowledge base offer conflicting advice or facts? Synthesizing information accurately from potentially contradictory sources remains a complex challenge for current RAG systems and LLMs. Beyond these, the pre-processing and maintenance effort is considerable. Your entire knowledge base, all those documents, needs to be carefully processed, chunked effectively, embedded, and then stored in that specialized vector database. That's a significant upfront task. And critically, this knowledge base then requires periodic reconciliation and updates to remain current. This is absolutely crucial for dynamic sources like legal databases, lists of local resources, or changing organizational policies, especially in the domestic violence space where information currency can be a matter of safety. Lastly, this whole retrieval and augmentation process inevitably adds some overhead. It can have a noticeable performance impact, potentially adding latency to the response time, increasing operational costs for embedding APIs, vector DB hosting, and utilizing more tokens in the final prompt sent to the LLM. All of these factors need to be carefully managed and optimized.
Yeah, and for a domestic violence crisis bot, these challenges feel amplified. Imagine the bot giving conflicting advice because two different legal aid documents in its knowledge base haven't been reconciled, or providing outdated resource information because the knowledge base hasn't been updated in 6 months. The dangers are very real. Misinformation in this context can be incredibly harmful, so you need to be acutely mindful of maintaining a high-quality, current, and consistent knowledge base. It takes ongoing time, resources, and rigorous processes for any organization. The reliability of your bot's advice directly depends on the quality and maintenance of its RG system. It makes this not just a technical implementation detail, but a core operational imperative. Okay, now let's talk about taking RG to the next level. Moving beyond just simple retrieval towards systems with even more intelligence, where the AI doesn't just retrieve information, but actually reasons about what it retrieves.
Yes, exactly. We're getting into more advanced patterns here. First, let's touch on Graph RJAC. This is an advanced form of retrieval augmented generation that utilizes a knowledge graph instead of, or sometimes in addition to, a simple vector database for information retrieval. A knowledge graph, if you're not familiar, uses nodes to represent entities like a specific type of abuse, a particular legal option, a named local support group, or even a specific local law or statute. And it uses edges to represent the explicit relationships between these entities. For example, an edge might connect financial abuse to legal aid resources for economic independence. This approach excels at answering complex queries that require understanding these relationships. It can navigate the graph, follow connections, and synthesize answers from information that might be fragmented across multiple documents, creating a more holistic, interconnected understanding of the topic.
Okay, so imagine linking different types of abuse, not just to documents, but to specific legal options, known psychological impacts, relevant local support groups. Understanding explicitly how they're all connected through these defined relationships in the graph, GraphRec could potentially provide incredibly nuanced responses for complex situations. It could maybe see the bigger picture of a survivor's multifaceted situation, almost like a digital detective connecting the dots based on those explicit links.
It's powerful, yes, but GraphReg comes with significant drawbacks. Building and maintaining a high-quality knowledge graph requires substantial complexity, cost, and specialized expertise. Graph modeling is its own field. It's also generally less flexible for handling rapidly changing unstructured information compared to vector databases. And navigating complex graphs can sometimes introduce higher latency into the retrieval process. So it's potentially superior for answering intricate, highly relational questions, but it comes at a much higher implementation and maintenance cost. The other major evolution is agentic AVRI. This is where an agent, a specialized AI component, another LLM perhaps, or a rule-based system, steps in to act as a critical gatekeeper and refiner before the retrieved knowledge even gets to the final response-generating LLM. It's not just retrieving anymore, it's actively reasoning about the retrieval process itself. This agentic layer significantly enhances the reliability and trustworthiness of the information extraction by actively interrogating the quality, the relevance, and the completeness of the data that the initial retrieval step found.
Okay, when you describe agentic RA validating sources and reconciling conflict, it almost feels like the AI itself is becoming a kind of critical editor or fact checker before passing the info along. What's the biggest aha moment you've personally had, or maybe a challenge you overcame, in actually teaching an agent to reason about its own retrieved information? It sounds complex.
That's a great question, and it really highlights a core shift in thinking. One aha moment for me was realizing that simply retrieving more context isn't always better. Sometimes retrieving too much just adds noise and confuses the final LLM. The real breakthrough comes when the agent learns not just to retrieve, but to actively filter, prioritize, and evaluate that retrieved context. For example, we had an agent working with internal policy documents. It kept retrieving an outdated draft version, alongside the current finalized version for the same policy query. The initial thought was just give the LLM both. But the challenge and the breakthrough was teaching the agent to not just see the different dates or file names, but to understand that a document labeled draft is inherently less authoritative than one labeled finalized. And then, crucially, to use that understanding to make a judgment call, discard the draft, only pass the final version. It's not just about finding information anymore. It's about evaluating its credibility, its timeliness, its relevance, much like a seasoned human researcher would do before citing a source. Precisely. So first, an agent excels at reflection and source validation. Let's say a user asks, what is our organization's current policy on providing emergency housing assistance? A standard RG system might pull up a blog post from 2020 mentioning an old policy alongside the official PDF policy document updated in 2025. The agentic RG layer, however, would analyze the document's metadata, like date, source type, file name conventions. It would recognize the 2025 policy document as the most current and authoritative source, and it would likely discard the outdated blog post before sending the correct, verified context to the final LLM. This ensures the answer is based on the official, current policy critical for crisis information. Second, an agent can be adept at reconciling knowledge conflicts. Imagine a crisis counselor asks the internal bot, what was the initial budget allocated for the new outreach program versus the final approved amount? The system retrieves two documents, an initial project proposal stating, say, a $50,000 budget, and a finalized financial report from the board meeting listing the approved budget as $65,000. An agentic RG component would identify this contradiction. It might be programmed with rules to prioritize finalized financial reports over initial proposals. It would select the $65,000 figure as the more reliable and finalized source and provide the LLM with that verified figure and context, ensuring the final answer is based on the most accurate, up-to-date data, not just the first piece of information it happened to find. Third, an agent can perform multi-step reasoning to synthesize answers to complex questions. If a user asks something complicated like, how do our local shelter's intake process and available counseling services compare to those offered by the Regional Women's Center? A simple RAG might struggle. But an agent could decompose this into separate subqueries. It might first initiate a search specifically for your local shelter's intake process documents, then a separate search for its counseling service descriptions. Then repeat those two searches for the regional center. After gathering these four distinct pieces of information, the agent would synthesize them, perhaps organizing them into a structured comparative format. For example, Shelter A, intake details, services details, Center B, intake details, services details, before feeding this organized comparison to the LLM. This enables a much more comprehensive, structured, and useful response than a simple retrieval could likely produce. And fourth, an agent can identify knowledge gaps and use external tools. Suppose a user asks, what was the community's immediate reaction on social media to our new public awareness campaign launched yesterday? The agent searches the internal knowledge base, which maybe only gets updated weekly with media reports, and finds no relevant information specifically about yesterday's launch reaction. Recognizing this knowledge gap, the agent can then activate an external tool, maybe a live web search API or a social media monitoring API. It uses this tool to find recent news articles or social media sentiment related to the campaign launch. The agent then uses this freshly gathered external information to provide an up-to-the-minute answer, overcoming the limitations of its potentially slightly stale internal database.
Wow, this agentic RA sounds incredibly powerful for the crisis response use case. An agentic RA crisis bot could potentially validate that a legal resource link it found is still current and not a dead link. It could try to reconcile conflicting advice it finds from different support group websites. It could decompose a really complex request like, what are my options if I'm experiencing emotional abuse, have no income, and want to leave my partner with my child? Into separate, targeted queries for legal aid regarding custody, emergency housing options, financial assistance programs, and mental health support resources. And then it could synthesize all that, maybe even use a live search to find breaking news about local law changes or newly available services that might affect the survivor's options right now. The depth and reliability of support this could potentially provide, it feels immense, giving survivors comprehensive, trustworthy, multifaceted information when they need it most.
It is potentially immense, yes. But the challenges of agentic RAG are also significant. It represents a substantial increase in system complexity and therefore costs requiring considerable engineering effort to design, build, and test these agentic layers and adding to computational expenses during operation. This added complexity can also lead to increased latency as the agent performs its cycles of reflection, validation, maybe multi-step reasoning or tool use before the final response is generated. Furthermore, the agent itself can become a new potential source of error. If its reasoning process is flawed or its rules for source validation are incorrect, it could potentially get stuck in loops, misinterpret tasks, or filter out the wrong information. But when implemented correctly and carefully, the potential improvements in reliability, depth, and trustworthiness of the answers it provides are often unparalleled, making it a powerful investment for truly critical applications where accuracy is non-negotiable.
Okay, so RA is already transforming many industries. We mentioned customer support, enterprise search. What's maybe a third, perhaps less obvious application that our listener could leverage this RA pattern for in their work?
Well, beyond the common ones like internal Q&A bots or survivor-facing info bots, consider research and due diligence automation for the organization itself. An agent could be tasked with compiling comprehensive reports on, say, specific legal precedents related to domestic violence cases in their state, or identifying potential grant funding opportunities based on current program needs, or even analyzing historical trends related to the effectiveness of different intervention methods reported in academic literature. The RG agent would retrieve relevant documents from legal databases, grant repositories, academic journals, synthesize the key findings, maybe even cross-reference information across sources to provide a holistic view. This could vastly accelerate the research process for the organization's staff, freeing them up for more direct service work. So all of these applications, internal Q&A on policies, consistent support using vetted FAQs for survivors, summarizing current news or legal changes, automating research are highly relevant to your goal of supporting domestic violence crisis response organizations. ARAG is about leveraging factual current information efficiently and reliably for both internal operations and direct survivor support.
Okay, let's get practical with some code examples again. How can someone actually start implementing RA? Let's begin with some built-in retrieval mechanisms available in the Agent Development Kit, the ADK.
Right. First, a really straightforward example provided in the documentation is simply using the Google Search tool. This tool comes directly from the google.adk.tools library. Using this tool within your agent is a clear instance of a built-in retrieval mechanism. It allows your agent to augment its internal knowledge by accessing external, real-time search results directly from Google Search. It's basically like giving your agent a direct browser search capability whenever it needs fresh public information.
Yeah, that seems like a great way for a quick start. For your crisis bot, you could use this for answering general, publicly available information questions. Like if a user asks, "What are the general signs of an unhealthy relationship?" Or "Where can I find basic information about restraining orders in the US?" The bot could use the Google Search tool to pull reliable information from vetted public sources like government websites or reputable nonprofits in real time. It's a good way to augment that foundational knowledge without needing to build a custom database immediately.
Exactly. Now, for a more structured and controlled approach, using your own curated knowledge, the second example shows how to initialize the Vertex AirRag memory service from the ADK. This service allows your agent to connect directly to a Google Cloud Vertex AI R corpus. A corpus is essentially Google Cloud's managed service for hosting your AG knowledge base, your documents, chunks, and embeddings. The code shows initialization with parameters like similarity topic A. This tells the service how many of the top most similar document chunks to retrieve for a given query. For instance, K3 retrieves the top 3 matches. It also shows vector distance threshold. This sets a maximum limit on the semantic closeness allowed for retrieved results. Think of it as a relevancy filter. If a piece of information in your knowledge base is too far, semantically distant, from the user's query, meaning it's not relevant enough even if it's the closest match found, the system will retrieve it. This helps prevent the LLM from getting confused by vaguely related but ultimately unhelpful information, ensuring the context provided is truly pertinent. This setup effectively integrates Google Cloud's robust, scalable RG functionalities directly into your ADK agent, supporting responses grounded in factual data pulled securely from your own curated corpus.
Okay, so this Vertex AI approach provides a much more scalable, persistent, and sort of enterprise-grade solution. It's specifically designed for managing your organization's own specific knowledge base, like that curated library of legal documents, internal support guides, or local resource directories you vetted. It means you're building a robust, secure foundation for your crisis bot's knowledge, ensuring accuracy and reliability derived directly from your trusted internal sources, not just the open internet. All right, now for you, our listener, remembering you're a Python developer with about 6 months of experience, likely familiar with some popular frameworks, let's walk through a complete RAG pipeline using LangChain. LangChain is a fantastic open source framework designed specifically to simplify building these kinds of LLM applications. This example will tie together many of the concepts we've just discussed into a working piece of code you could adapt.
Okay, let's break down this LangChain example piece by piece, keeping your background in mind. It starts naturally with data preparation. The code loads a document. In the example, it's a generic stateoftheunion.txt file. But you should imagine this as your organization's verified resource guide, maybe safety plan templates, or critical legal FAQs. Then, it uses a character text splitter. This is a LangChain tool specifically for breaking the document into those chunks we talked about. The example uses a chunk size of 500 characters and a chunk overlap of 50 characters. As we discussed, choosing the right chunk size is important, not too big for the LLM, not too small to lose context. And that chunk overlap helps ensure that meaningful information isn't lost right at the boundary between 2 consecutive chunks, maintaining the continuity, which is super important for things like step-by-step instructions or legal explanations. Next is embedding and storage. The code uses OpenAI embeddings. This component takes the text chunks and converts each one into a numerical vector. Those embeddings we discussed to capture semantic meaning. You can swap this for other embedding models too. These embeddings are then stored using a Weaviate client. Weaviate is an excellent open-source vector database perfect for this kind of task. This is where your bot's memory of all your vetted documents lives, indexed in a way that allows for that fast semantic search. Following this, the code defines the retriever. This is continuing to pull information from our vector store, the Weaviate database we just populated. It also initializes the large language model itself, in this case, Ch12-14, which will be used to generate the final human-like response based on the retrieved context. The retriever is essentially the smart search engine component for your custom knowledge base. Now, the core workflow logic is managed using LangGraph, which is LangChain's way of defining stateful, multi-step agentic flows. First, it defines a regraph state. Think of this as a container to holding important pieces of information as they flow through the process. The user's original question, the documents retrieved from the vector store, and eventually the final generation, the answer. Then it defines two main nodes, which are like steps in the workflow. The Retrieve Documents node takes the user's question from the state, invokes our retriever to get the most relevant documents, chunks, from Weaviate, and updates the state with these documents. The Generate Response node then takes that same question and the newly retrieved documents from the state. It uses a chat prompt template to format the input for the LLM. This template typically includes instructions like, you are an assistant for question answering tasks. Use the following pieces of retrieved context to answer the question. If you don't know the answer based on the context, just say that you don't know. This crucial step frames the task to the LLM and provides the factual grounding. Then it invokes the LLM, Ch12-14, to generate the final generation or answer, which is also stored back in the state. Finally, the code builds and compiles this graph using workflow.add node and workflow.adge. It links the retrieve node directly to the generate node, creating a clear two-step sequence. It also sets retrieve as the entry point for the workflow. So the process is, get the question, find the relevant facts from your knowledge, then generate an answer using only those facts. The app.stream call at the end shows how you'd actually run a query through this compiled workflow.
Okay, this entire LangChain pipeline, this is something you, with your Python background, can definitely build and adapt for your crisis bot. You'll take all your organization's verified critical information, those safety guides, legal FAQs, local resource lists, you'll chunk them up effectively, embed them using a model like OpenAI's or a free alternative, store them in a vector database like Weaviate or ChromaDB, and then you'll use a RAG chain or graph like this one to ensure that every single response your bot gives is not only empathetic in tone, but also factually accurate and current based on your trusted sources. Remember, getting those chunk size and chunk overlap parameters right during the data preparation phase is really key. You need to make sure you're pulling enough context to be useful without losing critical connections between chunks, but also not overwhelming the LLM's context window. This whole process, all right, is how you fundamentally ground your AI in verifiable reality. It's how you make it a truly trustworthy source of information, potentially a lifeline for those who desperately need accurate help. So the bottom line here with RAG is that it essentially transforms LLMs from closed book know-it-alls, that might be wrong, into open book reasoners that can leverage specific current knowledge. This vastly expands their utility and makes them genuinely reliable for critical applications.
Absolutely. To reinforce the key takeaways for RAG, it enhances LLMs by giving them access to external, up-to-date, and specific information that goes way beyond their static training data. It involves two key steps: retrieval, which is that smart semantic search for relevant snippets in your knowledge base, and augmentation, which is the process of adding those retrieved snippets directly into the LLM's prompt to provide context. RA significantly reduces the tendency for LLMs to hallucinate or make things up, and it enables the crucial integration of domain-specific, often proprietary knowledge like your organization's internal procedures or local resource lists. It allows for attributable answers, potentially with citations back to the source documents, which builds trust and accountability. And for more advanced needs, GraphRag and Agentic RAG offer even more sophisticated reasoning and refinement capabilities, allowing the AI to handle more complex queries and validate information, although they do come with higher complexity and implementation cost. This RAG pattern should really be your go-to rule of thumb whenever you need your AI agent to answer questions or generate content based on specific, current, or proprietary information. It's what makes AI reliable enough for critical applications like domestic violence crisis response.
Wow, what a deep dive today. We've really journeyed through 3 absolutely foundational agentic design patterns: exception handling and recovery for resilience, human in the loop for ethical oversight and partnership, and knowledge retrieval, or a RAG, for grounding in factual reality.
You should now have a much more robust mental roadmap, right, for building AI solutions that aren't just smart in theory, but are also resilient when things go wrong, ethically grounded with that essential human oversight, and always armed with the most accurate, up-to-date knowledge possible thanks to RH. These three patterns, resilience, human partnership, and grounded truth, they aren't just isolated techniques. They really form a powerful triad essential for any AI that's going to operate effectively and responsibly in high-stakes environments.
And just imagine the impact this understanding can have on your specific goal: supporting domestic violence crisis response organizations. Your AI agents can now be built to handle unexpected technical issues gracefully, ensuring continuous service even if a database hiccups. They'll have clear policies knowing exactly when to escalate sensitive, complex, or highly emotional situations to a human expert, guaranteeing that critical human empathy and judgment are always available when needed most. And, crucially, they'll provide survivors with information that is consistently current, accurate, and trustworthy, grounded in vetted sources via RG. This builds confidence in a system that's designed to help people at arguably their most vulnerable moment.
Exactly. These patterns empower you, even with 6 months of Python experience, to start developing AI solutions that truly augment human capabilities in this critical field, building confidence not just in the technology, but in the support system overall, delivering unwavering support where it's needed most. You're not just building chatbots anymore, you're building potential lifelines.
So as you go forth and start building these incredible, more robust tools, here's something maybe to ponder. How can we, as developers, as innovators, continually push the boundaries of AI agent reliability and empathy, especially in profoundly sensitive domains like crisis response? How do we ensure that our technological advancements always serve the most vulnerable among us with unwavering support and clear ethical foresight, not just for the challenges we see today, but for every complex, unforeseen challenge tomorrow might bring?
That's a powerful question to end on, and one we sincerely hope this deep dive today helps you to begin answering through your own groundbreaking work. Thank you so much for joining us.